Okay, so before starting, I got a question after yesterday's lecture. The thing you asked me about the Z bursts. So let me just clarify that. So this is what I wrote yesterday, that even neutrinos have a distance horizon, right? So if you have a very high energy neutrino with some energy E nu, it will eventually, at some energy, interact with a neutrino from the cosmic neutrino background, which has 0.1 electron volts or so. Let's take it as at rest. And then it will create a Z, and the Z will decay typically hadronically, but also through other channels. So it will create a burst of particles, including low energy neutrinos, by the way. So this is like a GCK cutoff, but for neutrinos. And just to clarify the energies of this, we can calculate them. Let's see if I can do it live. So this is E nu M nu. This is M nu 0. Sorry, this is. Let me do it differently. I want to say that this is P. Yeah, there we go. And this is high energy. Actually, let me just write it as 1, 2, 3. This should be MZ 0. Okay. So let's see if we do it correctly. So P1 plus P2. And this is neutrino, this is a neutrino, so P1 squared is M nu squared. That's also true for P2 squared. I'm going to expand this, so that gives me 2 M nu squared plus 2 P1 dot P2 equals D squared, which is mass of the Z squared. And what about this? Let's look at the four momenta. The only thing that remains is 2 E nu times M nu. So if you want to clear for M nu, let me make one simplification. The neutrino mass is very small, so I'm going to say that the square is 0. And what you end up having is that in order to hit the Z on shell, you need to have a neutrino of this energy. Okay, so does anybody know what the neutrino mass is? No, nobody knows, so it's okay. So this is like 91 GeV, the mass of the Z. The mass of the neutrinos, we don't know what they are, but 0.1 electron volts is an upper limit, very, very roughly. Something that also comes from like indirect effective neutrino masses from double beta decay and that sort of thing. So if you plug numbers here, it turns out that you need energies of roughly, I think it turns out like 4 times 10 to the 21. It should be it's like this. This is in GeV. So yesterday I said something like 10 to the 25 because I was putting a very convenient number for the neutrino mass, but it can be anywhere between 10 to the 21, like GeV, sorry, just to be GeV, and above. Those are the energies you need to hit that resonance. Those are energies that certainly for some models of astrophysical normal neutrino production or cosmogenic neutrino production, you may reach towards the end, low end of this. But if you now use a neutrino mass that gives you a resonance condition of 10 to the 25 electron volts or so, then you are no longer able to do that with normal neutrino production. Okay, is that okay? Yes, good. Good. Okay, that was it. Okay, so now for something completely different. Yesterday, I ended up talking about cosmogenic neutrinos and how we can jointly propagate them with the ultra-high-energy cosmic rays, and how we get the neutrinos out of the proton-photon interactions with the CMB and the extragalactic background light. But in doing so, I skipped through something on purpose, which is something I mentioned earlier about cosmic rays, which is that they have different mass combinations. So they are not just protons. In fact, we know they are not just protons. They are nuclei of different masses. And it is interesting to think about how we figure out that they have different masses, and how, not just that, but how we reconstruct the energy that the cosmic rays have at detection time. And I'm saying it's interesting because it is very difficult to do, but we do it, and in fact we have to do it if we want to find out what the sources of these cosmic rays are. So let me look into that, so at least you have an idea of how things are done. And you might have already seen some of the terminology that I'm going to show, but the basic picture is eventually the cosmic rays arrive at the Earth. We already solved the propagation equation, so we know how that happens, and they will hit a proton in the air. That interaction will initiate a shower. If the shower is initiated by a proton, it's called a hadronic shower because it has a high content of neutrons and pions in it. And then the pions decay further through the same kinds of processes we have been talking about before. The neutron beta decays, and so on and so forth. The positrons and the electrons will interact and create more photons. The final result at sea level, at ground level, is typically made up of muons and neutrinos. Everything else dies along the way. So the goal here is to find out from what we detect at ground level, so from the end products of this shower development, what was the incoming cosmic ray energy, and what was the identity of the cosmic ray. Was it a proton or something heavier than that? And there are clever ways of doing that. Oops, there had more. Yeah, so I'm going to talk about this in the context of the biggest cosmic ray observatory we have, which is the Pierre Observatory in Argentina. You might have heard about it. But first I want to show you the background behind this. So what is the fundamental theory behind reconstructing the energy and the mass composition? And for that, let's go back to someone we have mentioned before, Heitler. Okay, so I'm going to call this ultra-high energy cosmic ray detection. But I'm not really going to go into details about how the detectors work. It is just the theory behind it. So the basic theory is due to Heitler in 1954. Thank you. And if you want to look at it in more modern language, this is Matthews. This is a book, but this is a kind of a review and an update paper, Astroparticle Physics, 2005. Okay, so let's start not from a shower initiated by a proton, but from a shower initiated by a photon. That's called an electromagnetic shower. So it has most of its content as it develops in photons, electrons, and positrons, as opposed to hadronic showers. So this is the basic picture. We have an incoming photon, and then eventually it pair produces electron positron, and then those will radiate, and those secondaries or tertiaries will radiate further. The photons will again pair produce. So at each interaction, the number of lines is doubled, and in each one of the vertices. So let's separate this in levels. So this is the first interaction, the second interaction, the third interaction, and so on and so forth. Okay. The initial particle will have an energy of E0, and each of these interaction lengths, this is called the electron splitting length. And this is a quantity that, I'll show you in a moment, depends on the radiation length, so how long a photon travels before it radiates. Actually, what this quantity is let's see, it's actually what I said, yeah, that's fine. So the units of this radiation length are grams per square centimeter over square centimeter. So this is a column depth, yeah? So it's not just centimeters, but there's matter. This is traveling in the atmosphere, so there's a column depth of matter that these particles are traversing. And of course, the atmosphere has a density that is growing as you go closer to the ground, and that is taken into account in careful modeling. So this process of splitting continues until, at the very end, each one of the remaining particles at some point in the development has reached a critical energy. And that is the energy at which there is the maximum number of particles that the shower will have during its development downwards. For development of a shower in air started by a photon and containing many photons, this is roughly 85 MeV. Okay, and then when the particles on average have all of them the same energy, the shower then stops growing and it's not able to make more, significantly more pairs and significantly more photons, and then it starts shrinking. So let's see, why am I writing this? Let's put it here. So after n splittings, this is what we have. The depth that has been traversed, and by depth here I'm going to mean column depth. It's a quantity that is n times d. So we're going to do d n levels. So this is just this. And the number of particles in the shower is n, in big N, 2 to the power of the number of levels or splittings that we have had. So this is e to x divided by the radiation length. So at each level we're splitting in 2, that's where the base 2 comes from. Okay, so then we want to find out what happens at the maximum size of the shower. So at shower maximum, when we have reached the most number of particles that we will have, then shower maximum, the number of particles is n max, and each particle has energy of EC, the critical energy that I wrote over there. So each particle and that means that because we're starting from a single particle, then the energy of the primary, in this case a photon, is just that critical energy that each one of the maximum shower particles has, times the number of particles at shower maximum. So this is like a simple relation. But we know that, okay, let me write it this way. So because the number of particles at shower maximum is 2 times 2 to the power, of some critical number of splittings. So this is the number of splittings that this shower has had to undergo so that it reaches the shower maximum. This allows us to write, if you put everything together, that the number of splittings that you need to reach shower maximum, this is just ln max, ln 2. So this is E0 over the critical energy. Okay, we're almost there. So again, this is the number of splittings you have to undergo to reach the shower maximum. But the number of splittings is also some column depth, which I'm going to call x max. This is the column depth that the particles have to traverse in the atmosphere to reach shower maximum, divided by the length, the radiation length. And if you put this together, then using the definition of NC that we just found, or we just wrote, it means that the column depth that needs to be traversed by the shower in order to reach its maximum is given by this. And this is an important result. So we will use this in a little bit because this will allow us to tell whether the initial particle was a proton or a heavier nuclei. Even though we're starting with a photon right now, we'll see that similar expression will be used if we start with a proton. So X max, you will see it if you are exposed to cosmic ray stuff. That is a quantity that is often quoted as being directly connected to the mass composition of the flux of cosmic rays that the detector sees. Okay, so you're going to see in a moment why I started with a photon and not with a proton. Let me now do something similar. I'll try to skip a few steps, but now I want to start with a proton, not a photon. So it's more complicated, but the logic is very similar. By the way, is there any question about this so far? Okay. So again, we have an incoming proton, but now it will make pi zeros or pi pluses and minuses. Yep. And those in turn will, actually, let me make this a different color so it's easier to follow. So pi zeros will be red. These pi pluses will make additional neutral pions, and then they will also make other pions. Right? So this will continue decaying and making pi zeros and pi minuses along the way. I cannot capture the complexity of the shower in a drawing on the board. There's many, many more particle lines that I can't draw, but the general idea is that at each interaction step or each interaction length, you will get some fraction of pi pluses and minuses and some fraction of pi zeros. And remember from what we were talking before, the pi zeros decay into photons. So every time you make a pi zero, you make eventually, promptly, 2 gamma rays, and those gamma rays will each one start a shower like this one. So that's why I started with a photon initiated shower. So each one of these lines eventually becomes one of those, or 2 of those rather, once the pi zero decays. So the logic here is pretty similar as before. We start with an initial primary energy, and eventually once the shower has developed, we reach a point where the shower grows no more, and that happens when the average energy of each particle is some critical energy of the pions. I forgot this one. Let me write a few levels here. There's one extra bit of information you need, and that is that when the proton interacts, it doesn't just produce one pi plus and one pi zero. There's a multiplicity of production. So it produces many pi pluses, many pi zeros. The number grows with the energy of the proton. It's something between a handful at low energies, say at center of mass energies of 1 GeV or so, and then it grows to tens at 100 GeV or so. So we're talking about pretty large numbers, and I'm going to call that multiplicity. So the number of charged pions that are produced when the proton interacts, N charged, and the number of neutral pions is about half of that. Okay, not only that, but the energy that is given to the charged pions is roughly 2/3 of the proton energy, and this is the 1/3 that remains of the proton energy. Okay. All right, so far so good. So the cascade, as I said, it continues until we reach this energy, and this energy is reached at some level like before. I'm going to call N critical. That's when the shower is maximum. So let me write something like what I wrote there. After N lengths, which reminds me I didn't write what the lengths are here, so let me do that now. So this is this thickness here in the atmosphere, or the column depth rather. That's the interaction length. And it's again a quantity that is measured in grams per square centimeter. It's a column depth. Okay, and this is something we calculate, and actually this is the source of most of the uncertainty in shower development, because it depends on the proton-air cross-section, and I'll show how that looks in a little bit. So, okay, after N lengths, the number of charged pions is the multiplicity divided to the power of N, sorry. The total energy in charged pions is 2/3 to the power of N. Remember, at each step, there's 2/3 being given to the pi pluses, pi minuses. And the energy per charged pion is therefore just the initial energy of the proton divided by the number of pions that there are at that level. So 3, like this. Yeah, okay. Okay, so we can do a calculation similar to this one and find that the number of splittings that from here that we will need to reach the condition where each pion has on average this energy is, you can do it yourselves. I'm just going to write the result. So yeah, it's this one is 0 over the critical pion energy divided by this quantity. I just follow the same logic as I did for the photons. Okay. All right, so there's a little bit of a difference now between what happens when the shower is initiated by the proton and when the shower is initiated by a photon. When it's just a photon, everything that we have is, to first order, just positrons, electrons, and photons, so this is an electromagnetic shower. here we have that coming from the pi0 decays, but also the hadronic showers that contain more pions and more neutrons and more hadrons in general coming from the charged pions. So we need to account for both. And as I said, in practice, for detection purposes, what we see at the ground level is the muons that remain from the shower for the hadronic part and the light that is from the electromagnetic part. Okay, so let's write it that way. Okay, I'm going to use the central one because I want to keep this for a little bit. Actually, no, I'm going to use this one. I just need that expression. All right. So what I'm going to do now is find what we did before, the energy of the primary, but now for that shower, not for a photon-initiated shower. So there's two components. There's the hadronic component, as I was saying, hadronic component. And that is, we have a number of muons and muons, and each one has that critical energy that I wrote over there. Yeah, these are the muons that come from the pion decay. So to first order, they have that final state, final energy of the pions. And then there's the electromagnetic component. That is coming from the pi zeros decaying into gamma rays. So we have n max particles. That's the same n max that I wrote when we were doing the photon case. By particles here, I mean electrons, positrons, and photons. Each with the critical energy that I wrote before, EC. I'm just going to put an E here to distinguish it from the pion case. Okay, so this is what I wanted to reach, because then that means that if we want to find out what the energy of the primary proton was, we need to combine both the hadronic and the electromagnetic components. So the primary energy is E0. There's let me start with the electromagnetic one. Plus the hadronic part. Okay, so this is the main result. And what this is telling us is what I just said in words a little bit ago. You need to measure the amount of light, so the amount of energy in electromagnetic part, and the number of muons, which corresponds to the hadronic part. And adding those two will give you the initial proton energy. How does that happen? Well, that's where the detection actually matters. And I'm going to show a couple of slides about that. So you need something that can see muons and can see light, hopefully at the same time. If you just do one of these, you can only kind of put like an upper or a lower limit on the energy, so you want to measure both. And the Pierre Auger Observatory has actually detectors that will see both the components separately. So what you see there on the map on the left is the region in Malargüe, the southern part of Argentina, that contains at each position of the dot one tank like the one you see on the right, that is very well liked by the cows. They scratch themselves on the tanks. So this is a water tank, and when a muon comes in, it will create a chunk of light inside the tank, and then you can count the number of muons that reach the detector. Not just one of them. Typically, big showers in the atmosphere expand over tens of kilometers. These tanks are separated from each other like by 1 kilometer or so. So an extensive air shower, which is the name of the shower initiated by these protons, will hit an extensive number of tanks, hopefully. So you count the number of muons that each one of these tanks gets. You know more or less what the critical energy those muons have, but you can also more or less infer that from the light deposited in the tank. And on top of that, you see on the corners, here, well, there's 4 of them. There's 4 fluorescence telescopes. And those, let me see if I have a picture of that. Yeah, okay. Those are just, what I said, is that telescopes looking at the sky, and they will see the flash of fluorescence light that comes from the electromagnetic component of the shower exciting nitrogen in the air. The nitrogen will de-excite and emit photons, fluorescence, UV, that will be caught by the telescopes. So sometimes Auger is lucky enough that we will be able to detect the same shower both with the fluorescence detectors and with the ground level muon detectors. Most of the time is one or the other, but the golden events are the ones that they see in both channels, and those are the ones for which the reconstruction of the energy is best. Okay. So, let me see. Yeah, let me stop that here, and then I'll show that's the fairy tale part of the story, and let me just show you the nightmarish version of it. So, what is the problem with that? The problem with what I just wrote is something I alluded to in passing, and that is that we don't know what the proton air cross-section is, and that will matter in us modeling the development of the shower, because it's what determines how long a particle in general can go through air before splitting or creating more particles. So let me write it like this. The proton air cross-section that is that quantity lambda, sorry, interaction length is what I wanted to write. Okay, now we go. This is a quantity that depends on the proton air cross-section. And by that I mean this is a weighted average of proton, and proton with the different element, molecules that are in the air. So that's why I'm just calling it proton air. Times the average mass of a target in the air. And again, this is a weighted average. So the air is composed of not just protons, but there's molecules in it. So this we can measure. Well, not us, meteorologists, I guess, can measure it, or people that work in atmosphere physics. So this is the average target mass of air. And you need a model for the profile of the atmospheric matter density, which we have. So that one is easy. The hard part is, as you can imagine, this one. This is hard because this is the high energy. We need the high energy proton-proton cross-section to calculate this. And we don't have direct measurements of the cross-section at the energies we would like. So the current situation regarding the proton air cross-section is the following. Let me put here proton energy. In electron volts. And it's going to go from 10 to the 12 to 10 to the 20. Yeah. Let me see if I can do it. 13, 14. No, okay, this is a lot. Should be a lot better than this. Okay, this is as good as it gets. 13, 14, 15, 16. Ah, I missed one, sorry. 17, 18. Well, actually, it doesn't make much difference because we don't have much information here anyway, so I can just put 19 safely. Okay, and this is going to be the cross-section of proton on air. So this is centimeter square. This goes from 200 to 800, 3, 4, 5, 6, 7. So okay, and just to put some numbers here, this is the top x-axis. I'm going to write the equivalent center of mass energy for a pp interaction. So this is the root of s, and this is in TeV. Okay, so up to here is 0.1. This should be here 1. This is 10, and over here is 100. So just to get our bearings, the tevatron was roughly here. The LHC is roughly here. All right, so we, of course, can calculate from just theory what that should look like. And it looks like this. But this is mainly based on measurements of the cross-section that are over here. And that reaches up to maybe 10 to the 14 or so. Those are measurements done with collider protons. We have no good measurement of the cross-section beyond that. We had no measurement of the cross-section beyond that until the LHC turned on, and then we actually put some data points mainly over here. Okay, this looks still okay. The problem is this one prediction that I wrote here is actually one out of many possibilities. And the reason is it matters how these pions are formed in each one of the levels. And that's another way of saying it matters how hadronization occurs. And that comes with a lot of uncertainty. So what this line in white is showing is the result of one such hadronization model or hadronic interaction model. But that line could have been easily here from another model, and still fit the data of the cross-section measurements, by the way, fairly well, or here from another cross-section model, for another interaction model. So the main interaction models, just so that when you hear this, you know what it's talking about. They're called EPOS, Sybil. Let me write Sybil here. Surprisingly, they've been alive for years at this point, and all of them. So when you see predictions of these kind of things, people typically use the three of them, and then the systematic uncertainty is just the difference between their predictions, because we don't know which one is the most correct one. So the differences between the models grows with energy, and that is because that's where we need to extrapolate the most beyond the measurements that we do have. And that is precisely where also we are most interested in measuring the maximum, the reconstructed primary energy or the mass compositions we will see in a moment. So this is where things become hard. Extrapolations differ between hadronic interaction models. So the fundamental difference for modeling the hadronic interaction models. The development of showers in air is the fact that we don't know the proton-proton cross-section at the very highest energies. And that is shown by this. Okay, so bear that in mind. Now, there's one final thing I wanted to show regarding the shower development, and then we'll pause for a moment. And that is, I've been talking about reconstructed the primary energy, but I have been mentioning that we would like to also reconstruct what the mass of the primary was. And by similar arguments as the ones I laid out before for the energy of the primary, and I laid out the derivation in one of the exercises, you can find that the depth of shower maximum, this is a column depth of shower maximum for a proton initiated shower is X max for proton. This is the depth of the first interaction plus this quantity over here. And this quantity that I'm writing right now is the one that comes from considering both the development of the hadronic and of the interaction, and of the electromagnetic parts. So this is the same, let's start with this. This is the same photon interaction length that I had written earlier when we started with the photon. And this over here is the pion multiplicity that I was using when we were developing the proton-initiated shower. This is the critical electron energy, and this here is the depth of the first interaction in the atmosphere. So when the primary actually interacts. And you'll see that all the quantities that we have been mentioning before come into play here. Okay, so this expression holds a lot of information, and the reason is this is the result for a proton-initiated shower. So we, under some assumption of the hadronic interaction model, we can calculate x1, and then knowing how the shower develops, we can infer what X max is. We know now how to infer the initial energy of the proton, yes. So we can actually evaluate this quantity and see what the maximum energy, maximum depth in the atmosphere was. Or rather, what the depth of the maximum shower development was. Okay, but that's for protons. What happens if we have instead an iron nucleus interacting as a primary? Well, an iron nucleus is 50 or so nucleons, depending on exactly what the isotope is. Let's just count protons. It's 26 protons. And if we have a proton of energy E0 or an iron of energy E0, it's not the same, because for the case of an iron, each one of the protons will have E0 divided by 26 energy. And that means that they are less, each one of them individually is less likely to interact than a single proton that contains the full energy. So that means that they will take longer in the shower development to eventually trigger a shower. Conversely, if we have a higher energy iron, where each one of the protons that constitutes the iron has the energy of a single proton of energy E0, then that iron will interact higher in the atmosphere. So let me put in numbers what I mean here. So we have a proton of energy E0. it will interact at some depth in the atmosphere. If we have an iron of energy 26 times E0, then it will interact X max P at a depth that is smaller than the depth of a single proton. And that's because now you have 26 protons inside the iron, and each one of them has a higher energy. So the chances that any one of them interacts in the atmosphere are higher, and therefore it takes a shorter path length in the atmosphere for any one of them to initiate the shower. That means that if you get to measure what X max is for a single shower, let's say, and it is a small quantity, then that nucleus was likely to be a heavier nucleus than if it was a bigger X max. And that is what Auger does. So it takes, again, the number of muons detected and the amount of fluorescence light, and it can transform that into quantities that you can plug into these kind of expressions. So you have a collection of showers, you can infer statistically what the distribution is of X max and see if it looks more like the distribution of X max expected from a proton or from something heavier than that. And when they do that, they find that these measurements of X max are not constant in energy, but are actually have structure. And that means that the identity of the cosmic rays is changing with energy. So what they find is that as a function of the primary energy, this will go from 10 to the 17 to 10 to the 20, so the highest energies that they have, 18, 19. They use the interaction models, the ones there, to predict what X max could look like. For protons will need to travel longer, deeper in the atmosphere to trigger a shower, so they have a high value of X max, whereas iron doesn't need to go as deep, so it has a low value of X max. Those are just predictions. The data shows something like this. So light, actually this is more like medium or mixed, light and heavy. So what the measurements are saying is that at the lowest energies we have some combination of nuclei, and we can actually resolve what that combination is. Then it turns into mainly protons, and then it turns into mainly heavier stuff. These predictions are very uncertain. As I said, there is uncertainty in the interaction models, so these lines are really not lines, they're bands. And this line in red that I drew is just connecting dots with pretty huge error bars. So this claim of evolution from mixed to light to heavy is also an uncertain claim. But it is becoming more and more apparent that that might actually be the case. So just to show you how it looks in reality, okay, I think it's rebooting. Let's give it a minute. There you go. So this is how it looks in reality. So each one of these lines in different colors corresponds to a different mass group represented by protons, helium, nitrogen, or iron, and nuclei that have similar masses to those. And it kind of looks like a mess. And the reason is connected to what I said. The interaction models are uncertain. So if you look at protons, for instance, in red, just focus on the solid lines for one particular hadronic interaction model, then the amount of them is roughly, or the fraction of them is roughly 40% at low energies. Then it becomes dominated by them, and then the proton fraction becomes very low. Whereas the opposite happens for nitrogen, for instance, where as we go up in energy, the fraction grows and it becomes the dominant fraction at the highest energies. And as I said, the error bars on these are quite large because we have limited statistics to get this information from, but also because of this. Okay, so then the picture now is more or less complete. You know how the cosmic ray flux looks like at the Earth. It's a power law with some features. Then you know that the cosmic rays get deflected by extragalactic and galactic magnetic fields, and that needs to be taken into account if we ever want to do cosmic ray astronomy. And then you now know that the mass composition is something that we can measure together with the primary energy, but that the mass composition is not a constant thing. It's something that varies with energy, and that might be an indication of where the transition happens between galactic and extragalactic cosmic rays, and also about the nature of the cosmic rays themselves. But that requires model-dependent insight in order to get to that. We've been jumping between cosmic rays and neutrinos, and I want to come back and talk about neutrinos again and their connection to cosmic rays. And this, I think, there's a good way to close this. It's the ultra-high energy cosmic ray neutrino connection. And this is a powerful argument that allows us to estimate the flux of high energy neutrinos from the observed flux of ultra high energy cosmic rays without not needing to know any of the details about where they are made, the neutrinos are made, I mean, what the nature of the sources are, etc. So before I have been talking about cosmogenic neutrino production. Remember, that's when the neutrinos are produced along the way when the cosmic rays interact with the cosmological photo backgrounds. Now I want to not necessarily talk about those. The arguments that I'm going to make also apply to the possibility that neutrinos are made inside the sources of the cosmic rays themselves when the cosmic rays undergo similar proton-photon interactions, but inside the sources themselves. So with some radiation fields that exist inside the sources. So as I said, it's quite a generic argument. And this is an argument that is due to, oh, that's too big, Waxman and Bacal in 1997. Actually, it's 1997 and 1998. There's two papers where they did that. Okay. So then, as I said, the argument is if neutrinos are made by cosmic ray interactions, then by measuring the cosmic ray flux, we should be able to at least estimate what the neutrino flux should be. And let us focus on cosmic rays at the highest energy end. So this will be 10 to the 12 to 10 to the 10, sorry, 10 to the 10 to 10 to the 12 GeV. And remember the GCK limit means that cosmic rays with these energies reach us only from the local universe, say 100 or so megaparsecs around us. So we measure the cosmic ray flux with a Piero J observatory or some other detector. And from that, as we did yesterday, we can integrate that flux and measure the the energy, the luminosity in cosmic rays injected into the local universe. So I'm going to say Z of 0. Yep. So we've been jumping between cosmic rays and neutrinos, and I want to come back and talk about neutrinos again and their connection to cosmic rays. And this, I think, this is a good way to close this. It's the ultra high energy cosmic ray neutrino connection. And this is a powerful argument that allows us to estimate the flux of high energy neutrinos from the observed flux of ultra high energy cosmic rays without not needing to know any of the details about where they are made, the neutrinos are made, I mean, what the nature of the sources are, etc. So before I have been talking about cosmogenic neutrino production. Remember, that's when the neutrinos are produced along the way when the cosmic rays interact with the cosmological photon backgrounds. Now I want to not necessarily talk about those. The arguments that I'm going to make also apply to the possibility that neutrinos are made inside the sources of the cosmic rays themselves when the cosmic rays undergo similar proton-photon interactions, but inside the sources themselves. So with some radiation fields that exist inside the sources. So as I said, it's quite a generic argument. And this is an argument that is due to, oh, that's too big, Waxman and Bacal in 1997. Actually, it's 1997 and 1998. There's two papers where they did that. Okay. So then, as I said, the argument is if neutrinos are made by cosmic ray interactions, then by measuring the cosmic ray flux, we should be able to at least estimate what the neutrino flux should be. And let us focus on cosmic rays at the highest energy end. So this will be 10 to the 12 to 10 to the 10, sorry, 10 to the 10 to 10 to the 12 GeV. And remember the GCK limit means that cosmic rays with these energies reach us only from the local universe, say 100 or so megaparsecs around us. So we measure the cosmic ray flux with a Piero-J observatory or some other detector. And from that, as we did yesterday, we can integrate that flux and measure the energy, the luminosity in cosmic rays injected into the local universe. So I'm going to say Z of 0 here. And that is a number that is, yesterday I wrote it in ergs per second per cubic megaparsec. Now I'm going to write it in more particle physics units, in GeV per cubic megaparsec per year. There you go. Okay, so this is in the local universe. At a higher redshift, we can estimate how that looks like in a way similar to what we did in the past couple days. We assume that the sources of the cosmic rays are evolving, the number density is evolving with some factor that depends on redshift. And to keep things, I got it, general, we can write it in this way. So I'm going to write now the luminosity injected in cosmic rays at a redshift Z greater than 0. This is the one that we actually do measure from the flux that reaches the Earth. Times some factor that is going to be proportional to the number density of the sources of the cosmic rays at that redshift. So this is defined in such a way that f of 0 is 1. It's just a scaling factor. Okay, so from that, then we can write, let me first write it and then I'll explain the terms, but this is going to be the flux of neutrinos produced in cosmic ray interactions. Either by proton-photon or proton-proton interactions, both will give you neutrinos. This is E nu squared, so this is the energy flux of neutrinos. This is a factor that gives us a flux. It's a diffuse flux. The energy injection in cosmic rays that we just wrote over there. And then some factors that I'm going to explain in a moment. The conversion between time and redshift, cosmological time and redshift. This is just lambda CDM. And we integrate in redshift. This is the 1 plus C in the bottom is taking care of expansion. Okay, so this epsilon here, this is the fraction of energy, fraction of the energy in cosmic rays, so in the bulk of cosmic rays, that is given to producing pions. That goes into producing pions. And that's a number that is very uncertain. It could be 0.01, 0.1, 1. We'll see that when we fix it at 1, we get an upper limit on the flux of neutrinos. This one over here, F pi, is the fraction of the pions that are charged. This is something we know from simulations mainly. And this is roughly 0.5. And the last quantity here is the fraction of the pion energy that goes into neutrinos. And that one we can figure out quickly from this. So we have a pi plus, it will decay into mu. We've written this before, and then the mu decays like this. So at the end, we have each one of the 4 particles, 1, 2, 3, 4, more or less receiving the energy of the parent pion democratically. So we have 3/4 of the final, of the pion energy going into neutrinos. So this F nu is about 3/4 on average. And I should write here F pi. Okay. And like before, this dt dz is what we were using for the propagation equation earlier. So this is just Hubble parameter, 1 plus z. And you can just plug in the Hubble parameter. I'm going to write it here because we're going to use part of it. hz, Hubble constant. And I'm assuming lambda CDM, so I'll just have 2 of these. And for simplicity, I'm going to write it as h0 times small h, and you'll see why in a second. Okay, so if I plug all of this in to the equation, all these numbers and these definitions, then the flux of neutrinos becomes this. So this is E F F nu C 4 pi. There's an integral here between 0 and some maximum energy. I didn't write that there. This is the source number density, and in the bottom there's Hz 1 plus z squared dz. Okay. And typically this quantity is not plugged in directly, but we define the evolution of sources. We parameterize it by like a quantity like this. We just take the integral, same integral that you see here, but now we take that divided by the same thing and normalize it by the integral of just the denominator. Okay, I want to write all of this because that would allow us to put this in a simple form in a moment. And this number is typically something between 1 and 6, depending on what we assume for the source evolution of the number density of sources. So for reasonable populations, that is a number that is order 1. Okay, so we take all of that and we find the result that we want. The flux of neutrinos coming from cosmic ray interactions is, I'm going to write the first part, and then I'm going to evaluate it. This is at 0, so this is a measured quantity. These are the same quantities I have written the values for. So you know more or less what the size of this product is. 4 pi. This is the new parameter I introduced, and then that implies that I need to, I think this should be infinity here, yeah, to plug in this new integral here. Is that squared? No, it's fine, yeah. Okay, so these numbers, we know more or less the values of. We can calculate this. We can build a neutrino detector. Essentially, what you have is a source of neutrinos and a tank of water, which is just a collection of protons floating around. And the way it works is you seal that off so it's in perpetual darkness, and you put some light detectors inside. So you wait until one of the neutrinos that is emitted by the source hits a proton, makes a light signal, and then you say that was a neutrino. More or less, that's how it works. You want to put it as close as possible, the tank, to the source, because the flux of neutrinos is going down as 1 over the distance squared. You want to have as intense a source of neutrinos as you can. In this case, it's just nature fixing what the initial neutrino energy is, neutrino flux is. It's also nature fixing what the distances are between the sources and us, and they're very, very long. So the only thing we have a handle on is on this, on the detector itself. For high-energy astrophysical neutrinos. For reactor neutrinos and so on, we can actually move things and put them close to the source and have a more intense source sometimes. So the number of neutrinos that will interact number of interacting neutrinos. This is equal to the, I'm going to write it in words, the chance that one neutrino hits one proton, and that is fixed by nature, so that is weak interactions. That's just the cross-section of neutrino-proton interactions, times the number of neutrinos, sorry, the number of, the number of neutrinos that hit the tank, that reach the tank, sorry. And for that, in this case, we don't have the freedom to move the distance and put it closer to compensate from the L squared depletion. But we can wait longer, so we want to wait as long as possible, so more time, more neutrinos reach, and to of course, a high flux as possible, but in this case, the flux is fixed by nature, so we cannot move that around. And finally, the number of target protons in the tank. And that's something we can move. Yeah. So this is, if it's a tank of water, we can make it bigger. And that's something that is proportional then to the volume of the detector. The bigger we build, the higher the chances one of the neutrinos will eventually hit one of the protons. If we put that in an equation, then what I'm going to write is actually a very generic way of writing the number of neutrinos that interact in a detector, and just in general, the number of particles that interact in a detector, with details changing depending on the model. So number of neutrinos is the number density of nucleons, I'm counting now both protons and neutrons, times the size of the detector, the volume of the detector. I'm going to assume that we just count neutrinos from half of the sky. If it was the full sky, it would be 4 pi. And if you're interested in knowing why, just ask me afterwards. Times the exposure time, so how long you wait. The more you wait, the more neutrinos might interact. And then there's the integral. I'm going to say the integral is above 100 TeV. The flux of the neutrinos that reach the detector times the cross-section of a neutrino on a proton. And this is a deep inelastic scattering cross-section. At these energies, the neutrino will interact with one of the gluons or the quarks inside the proton or a neutron. So if you were to plug in for the flux the Baxman-Bacall upper limit, so 2.5 times 10 to the minus 8, and you demand that you get 10 neutrinos per year, then it turns out that you need a detector that has a size greater than about 1 cubic kilometer. And that is why IceCube and the current generation of detectors have about 1 cubic kilometer in size. And that is kind of lucky. The detectors were built based roughly on this kind of arguments, but we didn't know that this would hold, and they could have needed something bigger. So it turns out that this prediction was on point. Okay. There's a lot more to say about how neutrinos are detected, and this is interesting in itself. The 2 pi over here instead of the 4 pi means that the neutrinos are absorbed as they go through the Earth, and that in itself is a way to measure the cross-section of the neutrinos and the nucleons at very high energies. I haven't mentioned anything about using the neutrinos that we detect at IceCube, for instance, to do particle physics or astrophysics. But you see that already, the fact that we have the highest energies in neutrinos, so 100 TeV and above, that could allow us to do things like probing the existence of mediators that have a mass that otherwise we would not be able to reach with collider scale energies. So That's a whole different lecture, but for now, believe me, there's lots to do and lots that we're doing now regarding those neutrinos. So in closing, I just want to maybe take it a bit more personally. I remember being a kid and reading about, a kid like 10 years old, and reading about like astrophysics and cosmology and also particle physics in the same book. So, you go to the library, you found one of these books directed for teenagers, and it's all about the discovery of the W, the Z boson, and the expansion of the universe, all in the same book. And I found fascinating how the biggest scales, were connected to the smallest ones, and how one informed the other. And I never really got over the fascination. So you've seen in this series of lectures that we need we need cosmology, we need particle physics, and we need astrophysics in order to understand what's going on with cosmic rays, with neutrinos, and with gamma rays, of which I haven't said much. And every part is integral to the understanding of the whole picture. So this is one of those instances, like BBN, like gravitational waves, where all those scales come together. You cannot ignore one if you want to understand the other. So I hope at least I've given you a glimpse into that. I deliberately didn't do a lot of modeling of things in detail because I want you essentially to be able, with what I said, to have a semi-informed conversation with your colleagues that work on this. So if you get stuck in an elevator with one of them and they say cosmic rays, you should remember a few things. If you say neutrinos, you should remember a few things. That was my goal. But if you're interested in working on these for your careers, there's lots to do. There's data that is coming in now, and there's data that will come into the next 10 or 20 years. So it's a very active field. And with that, I thank you for your attention, and good luck.
Anything you would like to know to say? Yeah. So why don't you consider the whole sky?
Why don't I consider the whole sky? Okay, let's do it so quickly. So this is actually one of my favorite parts of the whole thing. At low energies, the neutrino interaction cross-section is negligible, right? That's why we say neutrinos just free stream once they are produced. But at high energies, that is no longer the case. And at the energies that we're dealing with, that is something we cannot ignore. So if you have the Earth, and you have your neutrino detector, let's say ice cube here in the South Pole, then starting from a diffuse flux of neutrinos that reaches the surface of the Earth isotropically, then the neutrinos that are coming into the detector from above are maybe going through a little bit of ice because ice cube is buried in the ice. But the neutrinos that are coming from the opposite side, they actually go through up to the diameter of the Earth, so more than 12,000 kilometers if they come straight from the center. So as I said, at low energies, it doesn't matter where they're coming from. They just reach the detector. At high energies, however, the cross-section is, the numerical factor is this, 10 to the minus 35 square centimeters E or GB. So it grows with some, I think it's just like 0.4 or so. In fact, the mere fact that this is not 1 already tells you that you are beyond the W mass pole. So this is an interesting thing in itself. Anyway, so the neutrino proton cross section grows up to a point where if you go through a fair chunk of the Earth, you will have a non-negligible chance of that neutrino interacting inside the Earth. So two things can happen. You can have either that neutrino undergoing a interaction mediated by a Z boson. So that looks like, let's see, Actually, let me just write it as a block, and then I'll expand it on it. So what you will have is a high energy neutrino and then a lower energy neutrino coming out of the same flavor. So what this does is it moves the flux of high energy neutrinos to lower energies because the outgoing neutrino now has a lower energy than the incoming neutrino. That is when mediated by a Z boson. So it's called neutral current interaction. And then the other thing that can happen is you're going through a fair chunk of the Earth and then the neutrino gets killed. And that happens instead when the mediation is by a W boson. So now you have, actually this should be X, I'm sorry. By that I mean like final state hadrons, neutrons, pions, whatever. In this case, you have a final state lepton, the same flavor, and then some hadrons here. And this is charge current. So in this case, you don't even have a final state neutrino anymore. You just are killing the flux of those neutrinos. So the end result is that at high energies, you end up seeing fewer and fewer of the neutrinos that go through the Earth compared to the neutrinos that just go through a little bit of ice. In the limit of my simplified equation, that means you only see one half of the sky. Yeah. In reality, what you can do with the fact that neutrinos get absorbed when they go through the Earth is to measure the cross-section of neutrino-proton interactions at energies that otherwise we would not be able to reach. Because you can compare the number of neutrinos that come from directions like this versus the number of neutrinos that come from directions like this. And the ratio of those two is an exponential function of the cross-section at energies above 10 TeV or so. And those measurements are the only measurements we can do to measure cross-sections at post-collider energies. And that's something that we have done before. But anyway, so that 2 pi hides a lot of information regarding what happens to neutrinos inside the Earth. Thanks for the question.